Good morning, everyone. This is Yuteng from National University of Singapore. Today, I'm glad to give a presentation for AtC and AtG conference with the topic of third harmonic resistance in ferromagnet and heavy metal bilayers. This presentation includes 4 parts. First, I will introduce the research background of this study. In condensed matter area, nonlinear transport behaviors becomes more and more important. For example, nonlinear Hall effects have been observed in the quantum materials with very curvature dipole, and such nonlinear response may eventually overcome the speed limitation imposed by the carrier's lifetime. Another emerging direction is the study of nonlinear swing current generation. In this regime, the generated swing current is not only linearly proportional to the injected charge current, but also contains a component that scales with the square of the current. Although most of theoretical works had predicted the presence of nonlinear swing current generation in certain materials, a reliable experimental method to detect such phenomenon is still lacking. So in magnetic hydrostructures, it's noticed that the nonlinear studies so far are more focused on the second harmonic spin transport signals. Second harmonic magnetotransport analysis is indeed a powerful tool for probing spin-related phenomena. Most notably for characterizing spin optical torques. Taking Hall signals as example, there are 3 main contributions in ferromagnetic hydrostructures. The first one comes from the field-like SOT and the altered field-induced magnetization oscillations, which can modulate the planar Hall effect and contributes to a second harmonic signal. The second contribution is the damping-like SOT, and it can modulate the HE. The last contribution comes from some electrical effects. Although all of these mechanisms contribute simultaneously to second harmonic magnetotransport, we can separate them according to the distinct angular dependence on magnetization and the magnitude dependence on external magnetic field. Beyond the SOT characterization, second harmonic magnetotransport analysis has also enabled the discovery of unconventional magnetoresistance. One representative example is the unidirectional spin Hall magnetoresistance. This nonlinear magnetoresistance originates from spin-dependent scattering at the ferromagnetic and heavy metal interface. The USMR is old with respect to the inversion of the magnetization and can be formulated by this equation. Additionally, the magnitude of USMR depends on the heavy metal layer and the applied current. However, experimental attempts on higher order signals are relatively scarce since it's foreseeably difficult to detect the much more diminished signal amplitude with the increase of harmonic orders. In this work, we systematically characterize the third harmonic resistance in polyalloy and heavy metal bilayers and shed some light on the understanding of nonlinear magnetotransport phenomena in ferromagnetic and heavy metal bilayers. Next, I will introduce the experimental methods used in this study and theoretical model for third harmonic resistance. In this study, all samples were deposited onto silicon oxide substrates using magnetron sparking at room temperature and fabricated into Hall bar using lift-off techniques. In situ magnetic field of 5 Auster was applied to induce an in-plane z-axis during the deposition. For magnetotransport measurements, an AC current was applied by a current source. The first and third harmonic voltage was simultaneously recorded by a locking amplifier. Concurrently, an external magnetic field was applied to the sample at room temperature using a slab system. The graph at the bottom right is a schematic diagram of the angular dependence measurements sweeping in the film plane, where phi represents azimuthal angles of the external magnetic field. Here we proposed that SOT-related third harmonic signals can be maximized by performing measurements under low field conditions. And next, I will introduce the derivation in detail. In our measurement, the magnetization of samples and the applied field lie in the film plane. Therefore, the total magnetic energy can be expressed in equation 1. And the angle of perturbation due to SOT effective fields can be written as equation 2. When the current flows along x direction, the field-like effective field and the outer field invariably points along y direction, as shown in the schematic diagram. By solving the differential equations, we can obtain the current modulator magnetization angle under low field regimes as equation 3. Since in plane anisotropic field HI is much smaller than the applied field under conventional measurement conditions, previous research used a simplified expression of equation 3 by assuming phi m equals to phi h. However, we cannot rely on this assumption because the magnetic field H poses the same order of amplitude as HI in this work. Equation 1 and equation 2 show the static first harmonic magnetoresistance which originate from AMR, SMR, and PHE. Under the modulation of current-induced effective fields, we replace phi m in equation 1 and equation 2 with phi m plus delta phi. Considering that delta phi is no longer small enough in the low field regime, we use up to the second order Taylor expansion for approximation. Since delta phi is linear proportional to the current, this expansion naturally leads to third harmonic resistance terms, as shown in equation 3 and 4. Now, in the presence of a nonlinear spin Hall effect, the generated spin current becomes proportional not only to the current I, but also to I squared. Here, eta represents the second order nonlinear index for semi-polarization. Consequently, the total field-like effective field is proportional to I squared, which further results in delta phi being proportional to I squared. By substituting this nonlinear angle modulation, delta phi NSHE into the first-order expansion term of the first harmonic resistance, we obtain the third harmonic resistance contributions originating from NSHE, as presented in equation 5 and 6. Similarly, under the SOT effective fields modulation, the second harmonic resistance, which originates from thermoelectrical effects and USMR, also contributes third harmonic terms after a first-order expansion, as shown in equation 9 and equation 10. Additionally, thermal-induced magnetization reduction or resistivity change can also give rise to third harmonic magnetoresistance. Here we summarize the magnetization angular dependence of different third harmonic contributions, where top panels corresponds to Hall signals and the bottom panels correspond to magnetoresistance signals. Taking Hall signals as examples, the distinct magnetization angular dependence of RxY delta phi square and RxY NSHE allow for their separation so fitting. However, further separating of the last two contributions require measuring the third harmonic resistance under different external magnetic fields. Another promising observation is that only third harmonic resistance contributed by nonlinear spin current show one-fold symmetry, while other contributions show two-fold symmetry. To better illustrate this observation, we simulate the third harmonic generation in the Bilayers structure with the presence of NSHE. These two figures show the angular dependence of the total third harmonic resistance with different values of second-order nonlinear index eta. Since the third harmonic resistance contributed by nonlinear spin current exhibits one-fold angular dependence, the difference between the total third harmonic resistance at phi m and phi m plus pi increase with the increase of eta. Now let's move to the results. First, we measure the third harmonic magnetoresistance in various layer structures for qualitative analysis. In ferromagnetic single layer, the third harmonic is solely from thermal-related contribution, which is independent on the external magnetic field and follows the same angular dependence as the first harmonic one. However, in heavy metal and ferromagnetic heterostructures, third harmonic resistance revealed a completely different angular dependence under H equals to 10 Oster in terms of both amplitude and shape. This observation further supports the existence of spin current-related third harmonic contributions in ferromagnetic heterostructures. At large field, such contributions are suppressed, and therefore the third harmonic resistance is dominated by thermal effects. Next, we will verify our theoretical model quantitatively by decomposing the different contributions in the measured third harmonic signals. Taking Hall response as examples, the amplitude of third harmonic resistance weaken quickly as H increase from 5 Oster to 100 Oster, which underscores the necessity of detecting spin current-induced third harmonic resistance under low field conditions. Another observation is that the measured third harmonic resistance shows twofold angular symmetry, which means the contribution from NSHE should be negligible in our sample. Taking the case when H equals to 5 Oster and H equals to 100 Oster as examples, we illustrate the deconstruction of third harmonic signals. One can find the data well fitted by our functions, which can be further decomposed into different contributions. Followed by the disentanglement of different contributions, we investigated how their amplitude varies with current and external magnetic fields. As shown in figure A and B, the linear dependency on current square is fully consistent with our model. Figure C and D shows the magnetic field dependence of different components, which allows us to further separate contributions that share the same angular dependency, as discussed in the theoretical model. From the linear fitting, we also extracted the corresponding intrinsic parameters. These values fall within the range reported in previous studies, thereby validating the reliability of our model. Finally, I will draw some conclusion about this study and provide a brief outlook for future work. In conclusion, we systematically characterized the third harmonic resistance in PYPT bilayers with angle-dependent magnetotransport measurements at different bias field and applied current. By considering the possible aforementioned spin current and the thermal-related contributions, we expanded the longitudinal and transverse resistance to the third harmonic orders and correlated with the experimental results. Considering that recent theoretical studies have predicted many material systems with NSHE, such as single-layer MBT, our work provides a portional method for screening materials with NSHE through symmetry analysis and quantitatively extracting the second-order nonlinear index through fitting. So thanks for your attention, and I would be happy to receive your questions.
So thank you very much for your very nice talk, Yuteng. So
Thank you.
I don't see any questions in the chat, but okay, Galen, please go ahead.
Hi, thank you for this very nice talk. So I saw you did some field dependence, and it looks like the signal reduces for higher fields. I'm just curious if you've done any temperature dependence, and if you think that you will see a similar reduction in signal for lower temperatures.
Yeah, I think the similar trend will also be observed at lower temperatures. But the difference is that at low temperatures, the in-plane enthalpy will also increase, which may give some let me show you the results. For example, at room temperature, the third harmonic curve in PT bilayer samples is something like this. If you lower down the temperature, the angle dependence may become something like this one. Because in tungsten samples, the in-plane anisotropy field is slightly larger, and I think lower the temperature in PT samples will also give the similar trend. So for such curves, I think it's relatively difficult to do the mathematical fitting.
Right, thank you.
Thank you.
Okay, so we are running out of time. So we will stop here. Thank you very much again, Yuteng.
Thank you.
With this, we finish the first session